All right. We have been talking about area on your last test. There was that one question about use integration to find the area, but it also said the area between the curve and the x-axis. That's all we've done so far. So we've taken any curve, okay, something, some nice f of x curve. Its bounds maybe would be intersecting from A to B. And then the area we're finding is the area trapped between that curve and the x-axis below. So we set that integral up from A to B, f of x, and then dx, showing that we are working relative to the x-axis. What we want to do now is find where the bottom isn't always flat. Okay, so right now that bottom base has always been the x-axis, so it's always been flat. So what do we do if we now introduce a new curve? I don't know if you can see this or not. Can you see that? And what if we wanted to do the area between two curved things? So the bottom is now curved instead of flat like the x-axis. It's really not that hard. It's quite simple. There are going to be different bounds. The bounds are going to be where the two curves intersect each other, not where they intersect the x-axis, but where the two bounds intersect each other. And if we call that new curve g of x, then the area that's red will be found as the integral from c to d of f of x, which is forming the shape of the upper boundary, minus g of x, which is forming the shape of the lower boundary, and we still have dx on there. Dx isn't necessarily telling me I'm touching the x-axis, it's telling me that the bounds c and d are in terms of x. They're not in terms of y, they are in terms of x. There's something that lines up with the x-axis or above the x-axis. So it's really just a simple subtraction between two things. You clean up the algebra in the middle, and then you do the calculus of doing an antiderivative. Suppose we were working with like a sine function. Okay, we know that sine function looks like this. And then suppose we'd overlapped into that sine function some kind of parabola like this. And we wanted to find the intersection of the area that was fully trapped between those two curves. Well, this area would maybe look like this. And so it has multiple intersection points. And that would be it. That would be the extent. So we would need to find each intersection point. So we call that intersection A, call that intersection B, C, and D. So there are 4 different intersection points. We would need to set up 3 different integrals. An integral that went from A to B, another integral that went from B to C, and a final integral that goes from C to D. So you're going to set up your area. We'll call it the total area. You're going to set up your total area this way. Let's start with the integral from A to B. The yellow function we're going to call f of x, and we'll call the green function g of x. So for the first region between A and B, the upper function, the upper boundary, is the f of x one. So I do it in the order of f of x minus g of x dx. The subtraction of the top minus the bottom. Clean up the algebra first. Then what happens between B and C? What's different? The yellow curve, the f of x curve, is now dropped below. And so when you do the integral from B to C, you have to switch the order because the upper boundary in that section is being formed by the g of x curve, and the f of x curve is the lower. And you'll have to figure that one out. And then finally, when we get to C to D, that region, it's back to normal again. It's back to the way where f of x is the upper minus g of x being the lower. So you're going to be tested on these questions in two ways. One will be without a calculator. When you don't have a calculator, either the intersection points are easy to find algebraically, or you're given a graph where they're already found for you. Then you'll have to do the work on your own. If you are given a calculator, it means that the bounds were not easy to find. And so you'll need to do calculate intersect to find them and store them in different alpha values in your calculator like I've showed you before. Okay, so grab your calculator a minute, and the store feature is above the on button. So you'll need to make sure you're familiar with that when you find the intersection of two things and you want to store it and call it intersection A. And then find the next one and call it intersection B, and find the next one and call it intersection C. On paper, you need to identify what A, B, and C stand for, like write down the decimal values, but then in your integrals, you can just call them A, B, and C if you've listed. So let me show you how to do that so that you know what the expectations are. All right, let's try this example. Let's try the two functions. Let's try y1 being e to the negative x, and let's try y2 being cos x. And we'll limit ourselves to the window of 0 to 2 pi. So go ahead and graph that a minute. Take a look at what the graph looks like, and then we're going to practice storing those intersection values in our calculator. So I'm going to pause the recording a minute while you do that. All right, so when we set up our window to 0 to 2 pi, and maybe going in a y from negative 2 to 2, we see the exponential function that comes down and hugs the x-axis. But then we also see the cosine function, which is above the above the function for y, and then it dips below, and then it goes back up again. So we've got a couple different regions. So we need to find the intersection spots. So we're going to find the first intersection spot, which is right here. So go to the second calculate feature. Okay, do intersect, and then focus in on that first intersection spot. So second trace, and then do the intersection. You should come up with 1.2926959.7. Okay, we're going to call that A. So somewhere on your paper, you would need to identify that A is equal to 1.2926957, as much as you can get, and then store that on your calculator. So at this point, you would quit from your screen. You would go to store, which is the button above on, and then take that answer and permanently store it in alpha A. Okay, so now A is set to that, and so your calculator will remember that. And then now let's find B. B is the next intersection point, so go back to your graph and find B. So we're going to do a second trace. We'll go back to number 5 as our intersection spot. We'll slide over to where they are intersecting again. And I compute, or the calculator computes that to be 4.7, so this is B, 4.7212928. Okay, again, write that down on your paper once, and then store that, so quit, store, and then do alpha B. So now it's permanently stored in alpha B. Would it be like, never mind? So I would do this on my calculator. I would do a math 9, 0 to A, oops, 0 to, come on, alpha A. Oh my goodness, alpha A. And then I would put in my two functions, boom, boom, and just let the calculator do it. You can do what? You can do, yes, yes, depend which order you put it in. I would have to do y2. I'd have to do y2 minus y1 dx. And then I could go plus math 9, alpha a to alpha b, and then I could switch the order, y1 minus y2, and then I could do it again. So you can let your calculator do all of it. Yeah, you can do that too. You can type it in, but sometimes those functions are going to be long. It'll be faster for you to just type in y1. Sure. Sure. All right, have a great weekend. See you Monday. Good luck to track. Good luck to tennis. Good luck to rowing. Say that again. So if you're doing, did you do all of them all together? Yeah. Let me see. Yep, that's exactly what I got.
You wouldn't